In this video, we shall look at differential equations of the following kind. We note that A and B are constants. Note the appearance of a function v. V in general is a function of x. Examples for v are exponential functions, trigonometric functions, or polynomials, terms such as x, x squared, x cubed, or any combinations of them. As we have mentioned before in our previous video, d is the differential operator d over dx. The general solution for such a differential equation consists of two parts. The first part is the complementary function that we are familiar with from our previous video. And we have another term. It's called the particular integral. And this particular integral is closely related to that function v. Now let's look at examples. Example 1. First, let's find the complementary function. Complementary function is a solution to this differential equation assuming the right-hand side is 0. To determine complementary function, we assume y is e to the power, say, lambda x. Lambda is a constant. Substituting the solution in here, we get lambda squared plus a lambda minus 6 equals to 0. Factoring it, we get lambda plus 3 lambda minus 2 equals to 0. The solution of which is lambda equals to minus 3 and 2. So your complementary function is an arbitrary constant a, e, to the power minus 3x plus another arbitrary constant b, e, now to the power 2x. Now we have to find the second piece, the particular integral, because the original differential equation has that term 2e to the power x on the right-hand side. So your function v is indeed that. In order to find the particular integral, we assume that the particular integral that we are looking for is closely related to that form. So we shall assume the particular integral y equals a constant h times e to the power x. So the first derivative, y prime, or dy, is just h ex as well. And the second derivative, which is d2y, is also h ex. So let's substitute this information into that original equation. d2y is h ex. dy is again h ex minus 6, y is h ex, equals to the right-hand side is 2 e to the power x. And you see that the common term will just go away, giving us 2h minus 6h equals to 2, or minus 4h equals to 2. So that means h is minus half. So there we have it. The particular integral is minus half e to the power x. Now we can find the general solution to this original differential equation. The general solution is this solution plus that solution, namely a e to the power minus 3x plus b e to the power 2x minus half e to the power x. That solves the problem. Example 2. We note that the left-hand side is the same as in example 1, so immediately you can write down the complementary function as a e to the power minus 3x plus b e to the power 2x. Now let's look at the particular integral. Particular integral, as we have mentioned before, is dictated by the right-hand side function. In this case, it is e to the power 2x. However, e to the power 2x is also part of the complementary function. So in order to make an assumption for a particular integral, we do the following. An arbitrary constant times x times e to the power 2x, which is the exponential function that appears on the right-hand side of the original differential equation. Again, we have chosen our assumed particular integral to be cx e to x instead of ce to the power 2x due to the fact that e to the power 2x is also showing up in a complementary function. So an introduction of x is inevitable in the assumption. So let's evaluate the first derivative, y of y prime, where y is given by that. That is just using the product rule, e to the power 2x plus 2x e to the power 2x. The second derivative, y double prime, which is that, is obtained by differentiating this with respect to x, so you're going to get 2e 2x plus 2e to the power 2x plus 4x e to the power 2x, which means it is c times 4e to the power 2x plus 4x e to the power 2x. Substituting this expression in here, this expression in here, and this expression in here, and equating that to 10e to the power 2x, we get the following. C 4x e to the power 2x plus 4e to the power 2x, so that's the first term, plus c 2x e to the power 2x plus e to the power 2x, that is that term, minus 6cx e to the power 2x equals to 10e to the power 2x. Let's compare both sides. So 4 times c, because it is multiplied by e to the power 2x, plus c equals to 10. So c is 2. As you can see, this plus that will just give you 0. So that means our particular integral is 2x e to the power 2x. So the general solution to the original differential equation is given by a e to the power minus 3x plus b e to the power 2x plus the particular integral 2x e to the power 2x. And that solves the problem. Example 3. As always, let's look at the complementary function. So it can be determined by lambda squared plus 2 lambda plus 5 equals to 0. So lambda plus 1 squared plus 2 squared equals to 0. So that means lambda plus 1 squared is minus 2 squared. So lambda plus 1 is plus minus 2i. So lambda is plus minus 2i minus 1. From our previous video, that suggests the complementary function is e to the power minus x, where this minus 1 is from the real part of lambda, times an arbitrary constant, let's call it a, cosine 2x, where this 2 is from there, plus another arbitrary constant b, sine 2x. Now let's do the particular integral. Particular integral is closely related to this function, so let's assume y is h cosine x plus g sine x, where h and g are to be determined. Y prime is minus h sine x, g cosine x. Y double prime is minus h cosine x plus, or minus rather, g sine x. Let's substitute this this, and this in here, here, and there. Upon that substitution, I'm going to get minus h cosine x. I'm going to write cosine x as cx as an abbreviation, minus g sine x, so that's that term, plus 2 dy, so 2 times this, so minus 2h sine x plus 2g cosine x plus 5y, so plus 5h cosine x plus 5g sine x, and that equals to 10 cosine x, because the right hand side is 10 cosine x. The coefficients of cosine x are minus h followed by 2g and 5h, and that must be 10. So the first equation is 2g plus 4h equals to 10, or 2h plus g equals to 5. Now the coefficients of sine x, there's one there, minus g. There's another one here, minus 2h. And the last one is 5g. Equals to 0 because the right hand side does not have any sign. Now simplifying this a little bit, you get 2g minus h equals to 0. The solution of which is g equals to 1 and h equals to 2. Note our original assumption, y was h cosine x plus g sine x for the particular integral. So since h is 2, you can put that there, and g is 1, and that gives you the particular integral. The general solution to this differential equation is therefore y equals to the complementary function e to the power minus x, a cosine 2x plus b sine 2x, plus the particular integral, which is 2 cosine x plus sine x. And that is the general solution to this differential equation. Problem 4. The complementary function is given by the following auxiliary equation, lambda squared plus 4 lambda plus 4 equals to 0. So factorizing it, you get lambda plus 2 squared equal to 0. So lambda is minus 2 minus 2. So that means the complementary function is given by ax plus b e to the power minus 2x. The reason to the appearance of this term is because the auxiliary function have common roots. Now the particular integral. Since the right-hand side is 8x squared, the assumption can be hx squared plus lx plus g. A polynomial with the highest degree is the same as the right-hand side of the original differential equation. So y prime equals 2hx plus L, and y double prime is 2h. Substituting this, and this inside this equation, we get that. Comparing the coefficients of the powers of x to the right-hand side, we can obtain the values of h, g, and L. And they are as follows. G is 3, h is 2, and L is minus 4. And that will give us the particular integral. H is 2, L is minus 4, and G is 3. The general solution to that differential equation is therefore y equals to ax plus b e to the power minus 2x plus 2x squared minus 4x plus 3. And that solves the problem. As always, thank you for watching.